So today we are continuing with studying curves. What is the plan for today? So first we will study self-intersections of the curves. So when we plot a parametric curve, when we want to plot an approximate picture of our curve, we must calculate few specific data for this curve, and one of the data is our self-intersections. So we'll see how to calculate self-intersections. This is really easy task. Then we will study how to compute the intersections of two different parametric curves. This is also a very easy task, but there are two interpretations. So we can compute those intersections. We'll get the intersections of the paths of those two curves. But it doesn't mean that if two cars are traveling along those curves, that they will really crash, because we have to interpret those intersections in appropriate way. Because if we want that they crash, then the intersection must be reached at the same time point. So there are two different notions of intersections of two curves. One is the intersection of the paths, and the other is the actual intersection, so in time. This is the first thing. And then we will study different parameterizations of the same curve. We already saw that a circle has many parameterizations, and now we will study different parameterizations, smooth ones and then singular ones. So we will see that smooth ones are those where we doesn't stop where there doesn't exist any point on our curve in which we would stop, in which velocity would be 0. But even if our parameterization is not smooth, that doesn't mean that the curve is not smooth. So there are two notions of smoothness. One is the notion of smoothness of the actual parameterization, and the other is the notion of smoothness of the curve. So we'll divide those two notions. And then the third thing, which you already know from analysis, but we will now be able to derive the equation for this, is the computation of arc length of the curve. So we have a curve, we choose two parameters, and we would like to compute what distance, what's the length of the arc the curve does in that between those two parameter values. So you will recall this formula from analysis. But this formula also gives us a notion of a so-called natural parameter. And this natural parameter will be very important when we will study curvature of curves. So we would somehow like to measure how curved our curve is at some point. So is it almost like that? Is it a straight line, or it's how curved it is? Is it like that, or is it like that? And so on. So we'll introduce a proper notion of curvature. And for this, we will need this natural parameter stemming from arc length of the curve. And then the fifth task for today will be approximately plotting a parametric plane curve without use of octave. So we will learn a technique which helps us to plot an approximate picture of the plane curve, and we don't need any computer tools to do this. And then the last two topics will be to compute areas bounded by the curve. So there will be two possibilities. Both of them, you know, from analysis. So one is if we have a curve, and then we would like to compute this area. So this is a usual definite integral. While the other thing will be if we want to compute for the same curve, we want to compute not the area below the curve, but the area which is traveled by the position vector. So this position vector travels along the curve, and we would like to compute this area. And we will see how to do this in the third hour of today's lecture, if everything goes smoothly. So this is the plan for today, and let's start. So the first topic is in self-intersections and intersections. So why I wrote self-intersections and intersections. So the first problem refers to self-intersection of the given curve. So let's say that we have some curve given by this vector valued function. And we would like to compute. So I will just take m is equal to 2 so that I can draw the picture. So this is f. This f traces some path, and then it intersects itself. And what we want to compute is this self-intersection. So this P is, this point is called the self-intersection. And why do we want to compute this self-intersection? This will be very important when we will sketch this parametric curve. So it's one of the characteristic things which we need to determine when we plot our curve is to determine what are the self-intersections of the curve. So, and let's take a specific example. And this is really an easy task. What we have to do, let's say that we take f of t is equal to t cubed minus 2t. This is the x coordinate. And then we have t squared minus t as a y coordinate. So how would we determine all self-intersections of this curve f? What do we have to do?
So when these two are equal?
Yes. So when these two are equal, you mean what are you referring to this?
So x coordinate and y coordinate should be equal.
Then we would compute only the points on this symmetral of the first and third quadrant. So if x is equal to y, then we are on this line. So this wouldn't really compute self-intersections. This would compute intersections with this line. So we would compute this point and this point. What in fact do we have to, what is our condition to determine the point P? Yes, so as Matits wrote in chat, both components need to be the same for different t. That's right, yeah. So we have to, the condition is that, so f of t1 f of t1 is equal to f of t2 for different t1 and t2. This is actually the self-intersection condition. So we are traveling, so let's say that we start at t equals to 0, and then at t equals to 1/2, and so on. These are position vectors at some time points. And this condition tells us that at time t1, we are in point P, and in time t2, we are again at point P. So this is the condition, this is the equation which we need, the system of equation which we need to solve. And this example is such that we can really do it by hand without computer. So otherwise we would need to use some numerical technique which we already know, technique to solve systems of nonlinear equations. But this example is such that we can factorize the equations and determine the exact solutions without numerical method. So let me write. So f of t1, this is t1 cubed minus 2t1, and then t1 squared minus t1. And this should be the same to t2 cubed minus t2. And then the second coordinate function is t2 squared minus t2. So these two conditions are the conditions for self-intersection. So let's write this in the more convenient form for us. T1 cubed minus T21 is equal to 2T2 cubed minus 2T2. And then T2 squared minus T2 is equal to T1, T1, and then T2 squared minus T2. And you can try to do some algebraic manipulation by yourself to determine what are all the solutions. I will show you one possible way how to solve this system. So one possible way is to notice that we will be able to factor out T1 minus T2 from both of the equations. So T1 minus T2 will in fact cancel out from both equations. To do this, I need to only rearrange the terms. So you see, if I switch those two terms, in those two terms, what I get is T1 cubed minus T2 cubed. I don't say that this is the only way to solve this, these two equations, but this is one of the ways. And you see, on both sides, I can now factor out T1 minus T2. And on the left side, I get, so you have to remember the formula for the difference of cubes. So it's a cubed minus b cubed is a minus b times, and then I have a squared plus ab plus b squared. And for us, a is T1 and b is T2. So I get T1 squared plus T1 T2 plus T squared. And on the other side, I just factor out 2, and I get T1 2 times T1 minus T2. So here, one of the solution of this equation is T1 is equal to T2. But I'm not interested in this solution, because if T1 is equal to T2, then I don't get a self-intersection because T1 and T2 are not different. Of course, if I will take T1 is equal to T2, this condition will be satisfied, but such solutions do not interest me. So I can here assume that T1 minus T2 is different from 0 and divide it out of this equation. So I can just divide T1 minus T2 out of this equation, and the actual condition is then what remains. So T1 squared plus T1 T2 plus T2 squared is 2. So this was the first one. And I repeat this procedure for the second one. And I get T1 squared minus T2 squared is equal to T1 plus T2 minus T2, sorry. And I can again here I have difference of squares, so it's just T1 minus T2 times T1 plus T2 is equal to T1 minus T2. And I can divide T1 minus T2 out of this equation, and what I get is T1 plus T2 is equal to 1. So what remains is this system of two equations. And what I can do now, here I can express T1 out of the second equation or T2 out of the second equation. It doesn't matter. For example, T2 is equal to 1 minus T1. And then I put this expression into the first equation. So then I plug this into the first equation. And what I get, so we get a quadratic equation in T1. So actually what we get is T1 squared minus T1 minus 1 is equal to 0. You can do this computation by yourself, but this is what we get. And we know how to solve. We have the formula to solve this quadratic equation, and we have two solutions for T1. So T1 is then, so first solution I will write T1 1. This will be 1 plus square root of 5 over 2. And then T1 2, the second solution will be the same, only that there is minus in the numerator. So 1 minus square root of 5 over 2. Okay, and then T2 1 is then, so we have T2 is 1 minus T1. I use this here. And what I actually get is square root of 5. What I actually get is 1 minus square root of 5 over 2. And T22 is then square root of 5 minus 1 over 2. Actually, so square root of 5 plus 1 over 2. Okay, so, and now what are our points? So point f of T1, 1. This is T1 cubed minus 2 T1 and you can check by yourself, but it is just 1. We get 1. So this is, I will just write it, t11 cubed minus t1. You can check that we get exactly 1. And also for the other coordinate. So also the second coordinate, it is t1 squared, t11 squared minus t1 is 1. So it's actually the point 1, 1. And also the other, so f of t1, 2. Of course, since our condition is that f of t1 is equal to f of t2, we should get the same point. Otherwise, it wouldn't be a self-intersection. So you can check that we indeed get 1, 1. And what you can notice here is that here we have the first solution of our quadratic equation. And then, so this is the first solution of our quadratic equation. And then we computed t2 out of the connection between t1 and t2. And the second solution of our quadratic equation, in fact, gave us the same solutions, only in the other order. So you see, only the order switched. So t11 is equal to t22, and t12 is equal to t21. So in fact, only one is important because the other one is only given in the other order. So the point 1, 1 is the only self-intersection of our curve, and it is reached for the values t1, t2 equal to 1 minus square root of 5 over 2 and 1 plus square root of 5 over 2. So the question in chat is, why is the second parameter t1 and not 2 t1 1? What did you mean by this? Can you explain a little bit more, or just ask, unmute yourself, please?
With the function like the vector 1, 1.
Mm-hmm.
So 1 equals to t11 cubed minus t1.
Mm-hmm.
How can that be just t1? If we put t11 in our function.
Sorry. 2 is missing. I see. 2 is here missing. This is what you wanted to say, right?
But that t1 is still t11.
1, 1, t11. Yeah.
Okay.
One.
Thank you.
Okay. Thank you for the observation. Yeah. So it's t1 is t11 in this case. Okay, and we don't know how this curve really looks like, but later on we will study how to sketch it, and I can just show you approximate sketch of this curve. Of course, I cannot explain how to get it because we would need to do a little bit of computations, quite a lot of computations to determine vertical tangents, then horizontal tangents, then asymptotic behavior, and self-intersection is one of the parameters which also tells us what's the approximate picture, what's the approximate sketch of our curve. And so you see 1, 1, this will be a self-intersection, and the curve looks something like that. This is just a sketch. So only for the curiosity, so what we would need to know that the sketch of the curve is exactly what I wrote. So we would need to determine this vertical tangent, then this horizontal tangent, then those intersections with x and y axis, and also the asymptotic behavior. If we have at least this information, those 6 pieces of information, then we can already draw approximate sketch of the curve. Okay, this was the first thing when we study intersections. And then the second is the intersection of 2 curves. So if you recall, so I wrote here self-intersections, and the other thing are intersections. So now we have 2 curves, let's say F1 and F2. And we would like to determine when do those curves intersect. For example, this is the sketch of the first curve. And then this is the sketch of the second. And we would like to determine those points of intersection. So what is the condition now to find those points? So which system do we have to solve? Yes, F1 is equal to F2, exactly. So we have to solve F1 is equal to F2. And the parameters do not have to be the same. So if we only study if the curves intersect, then T and S can be different, because we are only interested in the traces of our curves. However, if T represents time, and for example, this is the road traveled by one car, and this is the road traveled by the second car, and the question is whether those 2 cars crash, then the condition would be not only that F1 is equal to F2, but also T and S are the same. So F1 T is equal to F2 S. So this means that the curves intersect, while the condition F1 of T is equal to F2 of T means that the curves, the velocity, the vectors, the position vectors are the same at the same parameter. So these are two different notions of intersection, depending on what we are interested in. So in the first case, T and S doesn't have to be connected, doesn't have to be equal, while in the other, they have to be the same. And yeah, let's just do one example. We won't do the whole calculation, but only write an example. So let's say that f1 of t is equal to t squared minus 1, and then minus t cubed minus t squared plus 2 plus 1. And f2 of s is s minus 1, and 1 minus s squared. So we are interested in the intersections of those two curves. So f1 of t is equal to f2 of s. And you can do this for the homework. What we get is 3 solutions as expected, since this equation is since the equation of the highest order is 3. This is this one. We can expect that there will be 3 solutions, and the solutions are t is equal to minus 1, and when t is equal to minus 1, s must be 1. This is the first. And then the second is t is equal to 0, and then s is equal to 0. And the third is t is equal to 1, s is equal to 1. So here the point is we put minus 1 into the first equation, into the equation of f1. What we get is minus 1 squared minus 1. And the second coordinate is minus 1 cubed minus 1 squared. And then here minus 1 cubed, of course, then it gets plus. Here minus 1 plus 1. So what we get is the first coordinate is then 0, and the second coordinate is also 0. And then the other, let's say P1, and then P2 is, let's plug in now s is equal to 0 into the second equation, because it will be even less work. So since the equations are of lower order, so we get minus 1 for the first coordinate and 1 for the second. And the third point, you can check, it becomes so 0 and 0. So how to interpret those results? So the curves intersect in 3 points. In the point 0, 0, which is a double intersection, and then in the point minus 1, 1. But first, they do not. If this represents the motion of the cars, of 2 different cars, then those cars do not crash at times minus 1 and 1. But in the other 2 points, they really crash, because this happens at the same time. So cars crash at time t is equal to 0 and t is equal to 1. and the first crash happens in the point -1, 1. And the second happens in the origin. So this problem of determining the intersection, the self-intersections and intersection of the curves is very simple. We need to only to solve appropriate system of linear of non-linear equations. Okay, and this is a good point to finish this first hour. Is there maybe some question?
Yes, so I still don't understand why T1 and T2 should not be equal when talking about self-intersections.
So I will draw again this picture. So f of T1, so f is some map from an interval into R squared. And f of 0, let's say that f of 0, this is f of 0. And then position at time f of 1/2. And then position at time f of 1. And if you have more dense parameter space, then what we get is this curve. And what is of interest to us when studying self-intersection is if at some point we'll return to the point where we already were. So if something like that happens. So here it was ft1. So we came into this point at time t1, and then what interests us if f of t1 will be also f of t2 for some other time point t2.
So the okay, now I understand. So T1, T2 presents so are like time.
Yes.
Okay, thank you.
Because if of course if T1 is equal to T2, this condition will be met. But this doesn't mean that we have a self-intersection, because
so T1 equals T2 means that, so this is the same point.
Yeah, the same point, but also at the same time.
Yes. Okay, thank you very much.
Okay. Welcome. The question in the chat, yes, the cars crash because t is equal to s. If you interpret that t and s mean time, so so if the parameters t and s measure some time. Okay, then let's do 15-minute break, and we continue 10:17. So the second topic will be different parameterizations of the same curve. So different parameterizations of the same curve. And among all those parameterizations, one which will be of interest for us will be a natural parameter, so natural parameter. So let's first introduce the derivative of the vector function and see what the derivative means. So the derivative, we already saw the derivative of a vector function. Let's just recall what it means. So the derivative of a function, of a vector function, f, mapping from the interval into Rm, and this f has m coordinate functions. So this is defined in the same way as the usual derivative of a usual function, only that in the definition we have to know that all the quantities are vectors. So df in the point A is also f prime in the point A, and this is the limit of the differential quotient. So when h goes to 0, we're measuring this difference f of a plus h minus f of a over h. So this is the derivative of a vector function. So in our case, df of a is then a vector with components which are just usual derivatives of the coordinate functions. So the derivative of f1 in the point A, derivative of f2 in the point A, and so on. And what's the meaning of the derivative? So I'll draw a picture with m is equal to 2. This is a part of the curve around f of a. So let's say that this is f of a. Let's say that this is f of a, and then f of a plus h is, for example, I will write as if h would be big so that the picture will be more clear. So let's say that this is f of a plus h. And what we're in fact measuring here is this is the slope of this line. So f of a plus h minus f of a over h is the slope of this line. And in fact, if we interpret this for every coordinate function, we do this on every coordinate of our derivative. So this is the slope. Yeah, and so when h go in the limit where h goes to 0, we get the slope of the tangent. As we know, we get the slope of the tangent to this curve. The slope of the tangent to this curve. So we do this on every coordinate. So we get the slope of the tangent with respect to every to every direction. So the slope of the tangent in the direction of x-axis, the first of x1 axis, and then on the second component is the slope of the tangent in the direction of the second of x2. And so on. So what we get for the derivative, this is a vector. So in which every component tells us the slope of the tangent in the direction of this component. And what is actually then this derivative? So this derivative is in fact the velocity vector when we travel along our curve with respect to this parameterization f. So df of a is then is the velocity vector to our curve, to the curve, when we travel along its path, so its path with respect to the parameterization f. So df of a, this is the velocity when we travel along the curve with this specific parameterization. So with this specific f, if we change f, then we could be on the same curve and in the same point, but the velocity vector would be different, because this f, the parameterization really determines the velocity vector. So let's study a little bit how does this parameterization influence on this velocity vector. So let's say that we have some curve parameterized by f of t. And now I would like to ask you what happens. What would be the trace of our of the curve we travel if we travel with another parameterization, which is g of t is then f of t half. Let's say that this f goes from the interval 0, 1 into r squared. And let's say that we, here is f of 0. And here is f of 1. And let's say that here we have f of 1/2. And let's say that here we have f of 3/4. And now I take another function g. Now g will be a function from the interval 0, 2 into r squared. And g is g of t is f of t half. And my question is, what is the trace of g? Can you tell me what's the trace of g? Yeah, we would only get a part of the curve if the interval would be still 0 to 1, but I've changed the interval to 0 to 2, so that I really, when I calculate g of 2, I get f of 1. So yeah, but you in fact answered on my question. So nothing changed. The curve remains the same. Only the position in time is different, but otherwise I get the same trace. Okay, get the same trace, only that, so for example, here is g of 0, here is g of 2, and this f of 1/2 is now in fact g of 1, and this f of 3/4 is now g of 2 times 3/4, so 6/4. Okay. And now I calculate derivative of f in the point at parameter 3/4. And I get some velocity vector. So this is, let's say this is, I will draw this vector v, and I will draw it in the picture. It will be tangent to the curve. This is always the case. It is tangent to the curve. And now my question is, so this 3/4 corresponds to 6/4 in terms of g. And my question is, what can you say about dg of 6/4? What is the connection between derivative of f in the point 3/4 and derivative of g in the point 6/4? Yeah, exactly. dg is smaller than df, yeah. But how do we compare vectors? So we have to compare vectors. So when we have vectors, we must say something about the direction and something about the size, yeah. And it exactly, the directions are the same, yeah, but the sizes are 1/2. So the dg is 1/2 of df, because we are traveling along the same curve, but the velocity is twice smaller. I mean, the speed, the velocity refers to actual direction and speed. So the direction is the same, only the speed is half of the speed of the initial parameterization. So here we get 1/2 of v. So here we would have half of v. So you see, the parameterization, the message of this is that the parameterization, the same curve has many parameterizations. So the same curve has many parameterizations. The velocity vectors in the same point of the curve all have the same direction. But different length. Different length, and this length is in fact the speed of traveling along the curve. So the length is in fact the speed of traveling along the curve. And I said before that the velocity vector always points in the direction of the tangent. let's try to argue why this is true. So I will write this as a proposition. The velocity vector always points in the direction of the tangent to the curve. In the given point. So why would this be true? It's very easy to see. So we have f is our parameterization. Let's say that this is, I will just write this in the two-dimensional space. Let's take that m is equal to 2, because this is m is equal to 2 and m is equal to 3 is something which we can imagine and draw, but for higher dimensions, it's just a matter of definition. So I will write this just for m is equal to 2. So f of t is then x of t, y of t. And then by definition, f derivative of t is then derivative of x with respect to t and derivative of y with respect to t. And this is nothing else than the tangent to the curve. So if you have our curve around this t, let's say the t naught, we have this curve. And what is the tangent? By definition, the tangent is a line, which is which goes through f of t naught, and then plus k times, and then here this k is the slope, k times, and then this is in fact x of t naught, sorry, x of t naught. So then k times x minus x of t naught. And this k is, what is this k? This is the slope. So this is derivative of y with respect to x. So so this is in the xy plane, and so this x is now independent variable, and this y is dependent one. So we have here dy over dx. But if we regard y and x as a functions of t, we can here divide dy over dt and then dx over dt. This is what we can do with differentials. Why we can do this with differentials? Because differential is just the limit of the differential quotient. So if we would work with, so this is change of y over change of x, and we can here write change of y over change of t over change of x over change of t. So this is all discrete, no limits. I can easily divide by t, by the change of t in the numerator and the same in the denominator. But when I do the limit when when t goes to 0, change of t goes to 0, then I get what I wrote here. So differential of y over differential of t, and then differential of x over differential of t. But what's actually this differential of y over differential of t? This is derivative of y with respect to t. And then here we have derivative of x with respect to t. So this k is in fact this k, the slope is in fact derivative of y with respect over the derivative of x with respect to t. So in fact, this is just the slope of this vector. Let's say that this is the vector with coordinates x prime of t and then y prime of t. K is then the slope. K is the slope of this vector. This means that the tangent has the same slope as this vector, which means that the tangent really points in the direction of the derivative of f. So the tangent really points in the derivative in the direction of f prime t. I will have two questions. First, was this derivation clear? Okay, let's assume this was clear. So I was cheating a little bit here when I wrote that the tangent really points in the direction of f prime t. This is almost always true. When is this not true? And this discussion will, in fact, motivate our next definition. So this conclusion is really true almost always. There is only one case when this is not true. Does anybody see where could the problem appear? Okay, let's say that if we are at the end of the curve, in the end point of the curve, then we take, for the tangent, we take only the left limit, or if we are in the left end point, then we take the right limit. So this would be the problem, yeah, but let's say that we define the derivatives in the other way, in the endpoints. So the problem would be, so if the tangent is vertical, then there still wouldn't be a problem, because then what would hold for f prime of t? So this would be x prime of t. Yeah, so x prime of t wouldn't change. This would be 0, and y prime of t would be something. So if this f derivative of t would still could be 0, 1, or 0, 2, or something. So 0 something vector. But the problem would be if both coordinates of this parameterization would be 0. So this is true. So you were thinking in the right direction. Only so the problem would be if both of the components of the derivative are 0. This is true always, unless f derivative of t is 0. So if f derivative is 0, then the tangent doesn't the tangent doesn't necessarily the tangent could still exist to our curve. So if the derivative is 0, then this is not true, that the tangent points in the direction of f derivative of t, because that would mean that it's k times f derivative of t for some coefficient k. But if the tangent is not 0 vector, then this is not true. So the velocity vector always points in the direction of the tangent to the curve in the given point. So however, the proposition is still true, because if the tangent points in the direction of f derivative of t, then also the derivative points in the direction of the tangent. But this case, when the derivative is 0, then it still points in the direction of the tangent, even if tangent is not 0, because then it's 0 times the tangent. But the other way around is always true, even if f derivative of t is 0. Indeed, in that case, f derivative of t is 0 times the tangent. So this is still true. So the proposition, we don't need to change anything in the proposition. The velocity vector always points in the direction of the tangent. If it's not 0, then also the tangent points in the direction of the velocity vector. But if the velocity vector is 0, then it's 0 times the direction of the tangent. Okay. Okay, but we don't want such a parameterization where f derivative is 0, because then we don't know if the tangent exists. So let's first let's answer on a few questions. What does it mean that f prime of t, let's say f prime of t naught is 0 for some t naught? What does it mean that this is 0? Does it mean that that the tangent to the curve does not exist? So can anybody answer what does it mean that for a specific parameterization, the derivative at some point is a 0 vector? What does it mean geometrically? Yeah, that it means that the function is constant in respect to t at this point. But we said that f derivative represents the velocity vector. So this means, since the velocity vector is 0 at this point, that means that at this point we don't move in any direction. So for a specific point, for this instant of time, we don't move in any direction. So this means, this condition means, only means that at time t, at t is equal to t naught, the velocity vectors, so the velocity is 0 in every direction. So this doesn't tell us anything about the tangent. So this doesn't mean that the tangent doesn't exist. Let's see a few illustrative examples. For example, if you have a curve, a circle, so this circle is a nice curve. So nice, usually in analysis, nice means that it has derivatives in all points. Yeah, circle is a nice curve. We can calculate derivatives. It has tangents in every point. We can calculate the derivative everywhere along the circle. In fact, if we can calculate the derivative in one point, then it's the same for all points because the circle is symmetric. However, if we travel along the circle with respect to this parameterization, f of t is, for example, cosine. Last time we had t cubed and then sine t cubed for t between 0 and 2 pi. If we travel along the circle with respect to this parameterization, then let's calculate f derivative of t. What we get is, in the first coordinate, we get minus sine t cubed, and then times 3t squared. And on the other coordinate, we get cosine t cubed times 3t squared. And we see that f prime of t is equal to 0. For example, for t is equal to 0. So if t is equal to 0, then f prime of t is 0. Which means, so t is equal to 0, this corresponds to the point f of t is 1. So it's 1, 0. So it means that if we travel along the circle with respect to this parameterization, then in this point 1, 0, we will stop for a moment. So the speed of travel in every direction will be 0. So this means that in this point, we stop for a moment. The speed in both directions is 0. And so, but for other points, for other t's, this f derivative of t is non-zero, which means that everywhere else only on for t is equal to 0, we get a non-zero tangent. So this specific parameterization tells us that the circle is nice in every point, only maybe in point 1, 0. So for other points on the circle, f derivative of t is non-zero, which means, by the proposition above, which means that the tangent to the curve to the circle exist everywhere except maybe in the point 1, 0. So the circle is a nice curve only maybe in the point 1, 0 where our specific parameterization has a 0 velocity. But then, of course, there are parameterization of the circle where also this point 1, 0 is nice. So we have to look at other parameterizations. To determine the nature of this point. I will just write in the parentheses the smoothness. We call a point smooth. We call a curve of the point on the curve smooth if the tangent is non-zero. So to determine the smoothness of the circle in 1, 0. So one other parameterization would be cosine t sine t. So for this parameterization, cosine t sine t, even in this point 1, 0, we would get a non-zero velocity vector, which means that the curve is smooth also in this point 1, 0. So this discussion motivates two definitions. A parameterization f is smooth in the point t naught, is smooth in the point f t naught if f derivative of t naught is non-zero. So this is smoothness of the specific parameterization, while a curve C is smooth in the point A if there exists some parameterization such that so some parameterization, let's say G, such that G derivative of T naught is not equal to 0, where G of T naught is equal to A. In other words, a smooth curve has tangents in all points. So these are two different notions of smoothness. Smoothness of the curve, which doesn't depend on the parameterization, and the smoothness of the specific parameterization. And smooth curves are something which are nice to work with. If the curve is not smooth at every point, So the points where the tangent to the curve doesn't exist are called singular, and to study the nature of the curve around the singular point requires more work. So let's define also this point of the curve which are not smooth. Are called singular. Okay. And now my question is, do you maybe know or do you recall some curve which is not smooth in every point? And we already mentioned this curve today at the beginning of the first lecture. So does anybody remember one curve which is not smooth? And then we will try to justify why it's not smooth at the specific point. So it has something to do with bicycle. If you remember, we had this curve which described the motion of the valve when we travel along the x-axis with the bicycle. So we got this cycloid, yeah, cycloid. So I will just motivate the beginning of the next hour. Example. We had the cycloid. The definition of the cycloid was f of t. Let's take that the radius of the wheel is 1, which means that then it's t minus sinus t, sine t, and then 1 minus cosine t. This is the parameterization, one specific parameterization of the cycloid. And let's recall the image, the trace of the cycloid. So it's somehow it's this curve. So is this a smooth curve? We know from above that the curve is smooth if there is a parameterization such that the derivative in this point is not 0. So we have here one parameterization, one specific parameterization of the cycloid. And let's see what can we infer from this specific parameterization. So f derivative of t. What's f derivative of t? So it is 1 minus cosine of t, and then sine of t. And we see that when can be this 0? So f derivative of t is non-zero if and only if t is not equal to 2k pi, where k is a whole number. So this parameterization tells us that all points except the points of the form 2k pi are smooth points of this curve. So the problematic points are only those points. So all points except a0, a1, a2, a1 minus 1, so except ai, where I goes through whole numbers, are smooth. What about AIs? So this parameterization tells us that the only problematic points, so the only points which could be singular are those a minus 1, a naught, a1, a2. However, we have to justify that those points are really problematic, so that there doesn't exist other parameterization of the cycloid such that the velocity vectors would be different from 0. So the question is, does there exist a parameterization of the cycloid such that the velocity vector in these specific points would be non-zero? So this is the question, and let's think about this question a little bit, and we will solve this question first after the break. So to finish this hour, is there may be some question? Okay, otherwise we continue in 15 minutes. So we stopped the last hour with the question if the points of the cycloid in which the velocity with respect to this specific parameterization is 0 are indeed problematic, are indeed singular points of the cycloid, or is only the parameterization not appropriate? What would you say? What do you think? Are those points really singular, or can we compute the tangent to the line, to the curve? Yeah, in fact, here we can see from the picture that the tangent is really, won't exist. But we have, of course, we have to somehow, I mean, it could be like that. It could be the tangent could be, it could happen that the tangent would be vertical here. But let's try to show that the tangent here really is not, cannot be computed, that the slope can really not be computed. So we conjecture that the slope, that the tangent really doesn't exist. Which means that we cannot compute its slope. Okay, before we said that what's the slope? The slope of the tangent is the change in, so it's dy over dx. And it's just dy over dt, because differentials behave like usual fractions. So dy over dt, and then in the denominator, you have dx over dt. And so let's try to compute left and right, the right slope. So the slope from the left and the slope from the right to this curve, to our cycloid. So let's try to compute limit when t goes to 2k pi, let's say 2 pi, or we can leave 2k pi of this slope. This is y derivative of t over x derivative of t. What we get is the limit when t goes to 2k pi, and then we just derive this equation of the curve. We already have this, so it's sine t over 1 minus cosine t. And what type of derivative is this? So we have in the numerator, we have sinus of 2k pi, this is 0. And in the denominator, we also have 1 minus 1, which is 0. So it's 0 or 0. We cannot compute such a limit. But there is a way to try to compute such a limit if it exists. And this is L'Hopital's rule. So let's use L'Hopital's rule. So it's limit when t goes to 2k pi, L'Hopital. So we have to differentiate both numerator and denominator. We get cosine t in the numerator and sine t in the denominator. Okay, and what we get? So in the numerator, we get 2k pi, so cosine of 2k pi. When we go to, for example, 2 pi from the left, so if we draw a circle, this is the best thing to visualize cosines. So let's say that we do 2 pi once a circle, and then we come to this point. So cosine will be 1. Yeah, okay, here is no problem. So cosine will be 1, while the sine will be here approaching 0 from the negative direction. So it will be minus 0. So this will be, in fact, minus infinity. Okay, and if you repeat this calculation for the t's which fall to 2k pi, so t's which limit in 2k pi when the right limit in the point 2k pi, so everything is the same, only that here we have t falls to 2k pi, cosine of t for sine of t, and this is still 1 in the numerator, while in the denominator we are going to 2k pi from the positive direction. So sine will be plus 0, which means that we get infinity. So we got that if the tangent exists, then its slope should be minus infinity, while on the other hand, it should be infinity. So it just doesn't exist. This means that we cannot calculate the tangent to this curve in the points 2k pi, which means that those points are really singular points. So the tangent to our curve in the points t is equal to, in the points corresponding to, points corresponding to t is tk is 2k pi, where k is a whole number, really don't exist. They are so-called cusps of our curve. So infinity and minus infinity describe the same direction. That's true, but on one side, the velocity should go from minus infinity to infinity instantly. So when we are approaching this singular points, the tangents are negative, so have negative direction. They go to minus infinity, but then when we go from the right hand side, they fall. So they grow to infinity. So the velocity vector should change from minus infinity to infinity instantly, which is not possible. So there won't exist any parameterization where the velocity could, so the velocity in the parameterization, here it will go to infinity, but then it should jump to minus infinity. So it cannot be done smoothly. There won't be a parameterization where we could do this change in velocity vector smoothly. Because yeah, if you remember the definition of the so if we look at the usual curve, let's say one curve with the singularity. So you see what's the differential quotient f of f derivative in the point a. This is a, so it's f limit f of a plus h minus f of a over h when h goes to 0. And you see when we go for h smaller than 0, the left limit is minus infinity, while for h bigger than 0, so the right limit is infinity. So you see the velocity cannot change from infinity, from minus infinity to infinity for no parameterization. Because so we cannot choose. It looks like that we could draw a tangent like that. Yeah, it looks like, but when we calculated the left-hand side derivative, we calculated just one derivative, so we cannot smoothly. It would mean if this would be really a tangent, this would mean that we could continue this somehow. Yeah, it has to do something with deep algebraic geometry, with resolution of singularities. If this would be really smooth, if we could do this smoothly, then it would be possible to somehow resolve this singularity so that it becomes like that. So then we could really, so resolution of the singularity. That we could do this transition smoothly, but this is not possible to do because here in this point the slope is infinite, and if you do this resolution of the singularity, there would be no point where the slope would be infinite, and here again infinite. So it's not possible to do this. So when you try to determine if the point is smooth, you just calculate these limits. Y prime t over x prime t for appropriate t, and you calculate both left and right limits. And if the left limit is the same to the right limit, then it means that you would be able to do this resolution of the singularities. So somehow continue this motion smoothly. But yeah, we got left limit is different than the right limit, so this is not doable. The same problem would be so we have like that and like that. Even this point would then be singular point. However, such curve, this is what we would need in this point to be so to be smooth. If you have definition of the curve on the left and then the definition of the curve on the right, then it is a smooth point. So where they meet is a smooth point if both derivatives are the same. So the left derivative and the right derivative. Okay. So these points of the cycloid are really cusps. There doesn't exist a parameterization which would be smooth in these points. Okay, this is the notion of smoothness of the point and the smoothness of the parameterization. And now we come to the notion, the third topic of today's lecture, which is arc length. And the natural parameterization. So we would like to measure the length. We have our curve. And we would like to measure this length. Let's say that we choose here parameter T1, then we choose here parameter T2, and we would like to measure this length, this distance traveled along the curve. What is the distance? What is the length of the arc? In fact, you will, when we will derive this formula, you will remember it from analysis. So the idea is to divide this arc into small intervals. Okay, maybe I should better write here T. Let's say that this is B, the endpoint, and then this T1 is A, the left endpoint. So we divide this arc with on the intervals T1, T0, T1, T2, T3, and so on. And for example, this is the vector f of T1, f of T2, and this is the vector f of T3. So this is f of T3 and f of T2. And we know what's the length of this f. We approximate the arc length between T2 and T3. The arc length between T2 and T3 is approximately the norm of the vector f of T3 minus f of T2. So f of T3, f of T1, this is this vector, which I cannot draw because it will be too dense. So I will draw here, draw f of T2 and then f of T3. I will draw here this vector. And this is exactly f of T3 minus f of T2. And we approximate this arc length with the norm of this vector. So the arc length is then approximately the sum of all those vectors f of Ti plus 1 minus f of Ti when I runs from 0 to n minus 1. So we are in fact summing up those chords on this division. And now these chords are in fact we can in fact calculate these chords by approximating. So let's do let us do a linear approximation of f in the point f of ti. So what is the linear approximation? This is just the tangent to the curve in the point f of ti. What we get is then linear approximation. So linear approximation in the point t is then f of ti plus then the derivative in this point times t minus ti. So this is a linear approximation to the curve in the point ti, and we plug in ti plus 1, and what we get is f of ti plus f prime of ti times this ti plus 1 minus ti. And this is our approximation for f of ti plus 1. And let's write this difference between ti plus 1 and ti. Let's write this as difference between ti's. So ith difference between ti's. So what we get is we put this on the left hand side, and what we get is that f of ti plus 1 minus f of ti is approximately f derivative of ti times this difference between consecutive t's. And here we are interested in the norm of this. So we take the norm of this. So it's the norm of the velocity vector. And this difference in ti's is just some number. And it's positive number because ti plus 1 is bigger than ti. So it's just some number. And when we plug in here into our arc length approximation, we get that this is approximately sum when I goes from 0 to n minus 1. And then we're summing up norms of the velocity vectors times this difference in ti's. And now when we send the differences between ti's to 0, so for every I we send these differences of ti's to 0, which means geometrically that we really do a dense division of the arc, which we want to calculate its length. What we get, so does anybody see what we get here as a result of this limiting process? So this is the definition of one limiting process we studied in analysis. Yeah, we get exactly Riemann integral. That's true. That's true. So this is just the Riemann sum for the integral of the function norm of f derivative of t dt when t goes from the left endpoint, which is A, to the right endpoint, which is B. So this is true because this sum on the left, this is the Riemann, this is the Riemann sum of the function norm of f prime t on the interval a to b. So it's just the definite integral of this function. Yeah, this is we made a linear approximation, yeah, but since we did this, we did the limiting process in the limit, those linear approximations will be in fact a proper approximation. So that will in fact measure the true length. So yes, here we did a linear approximation. Here we did a linear approximation, but when ti plus 1 minus ti will be small enough, this linear approximation will be exactly the distance. So it will be exactly the arc length. So this linear approximation is in fact then in the limit, it's the proper quantity which measures the distance, the length of the arc. So this is the arc length. Let's write. So the arc length of f between a and b is integral of the norm of the velocity vector when we travel from A to B. Probably you remember this from analysis. So if I recall correctly, then last time I said that we will stop 15 minutes earlier this time because we were, I took you a few minutes every few last weeks. So we will shortly finish. Let's just look at one example. So how we measure so how would we calculate the length of the cycloid traveled in one turn? So example, the length of the length of the arc when wheel moves for one full turn. So this means that we are interested in exactly the length of this part, because of one of these loops. Because then we start, the valve starts at the bottom, and then it moves, and it moves exactly for then it when the wheel moves for does one full turn, then the valve again ends here at the bottom, so at y is equal to 0. So by this formula, what we want to compute is our f of t, our cycloid. Let's remember again that it's t minus sine t, and then 1 minus cosine t. So here t was 0, and here t was 2 pi. So what we want to calculate is integral of from 0 to 2 pi of the norm of the derivative. So of the norm of the derivative, which is 1 minus cosine t, and then sine t. This is what we want to compute, and this is integral of 1 to 2 pi of 1 minus cosine t squared plus sinus t sine t squared, and everything under square root. Okay, this is what we want to compute, and the exact computation, you will find the exact computation on page 12 of the handouts, but you can do it by yourself. So here, from here on, it's only computing with, and you have to use some trigonometric identities to evaluate this integral, but you get 8 at the end. For the exact derivation, you're welcome to look in the handouts. Okay, and let's really finish for today. Are there maybe some questions